few number of people in the classroom today and see if we have some others to join us. So today we're going to focus on calculating textures, look at the mathematics involved in that. So we'll go back to spherical harmonic functions that we introduced with spherical indexing. And again, like usual, please let me know if you have questions as we're going through the discussion. All right, so references, I have a few that I'm starting with. Bunga, this red book, Texture Analysis and Material Science, this is a very mathematical book. So if you're interested specifically in the mathematics of crystallographic texture analysis, this is a good place. It's not an easy reading book. It's a difficult book. It has a lot of very in-depth mathematics that are involved in the calculations. A couple of others that I've shown here with Dillamore and Roberts and Tinkoff. And then down at the bottom, I've mentioned any of the ICATOM series. That's the International Conference on Texture of Materials. That's held every 3 years. It's something that just barely completed in the first week of July this year. So it's just barely completed. And the next one is going to be in Rio de Janeiro 3 years from now. So not scheduled, of course, yet, but it'll be 3 years from now approximately. All right, so another reference that is more easily readable is Cox's book, Fred Cox, on texture and anisotropy. This book is now, let me see if I see the publication date. It's now probably 20 years old. The Bunga book was from the mid-60s, late 60s. This book is maybe 20 years old now. Again, it goes through some of the mathematics, but not in quite as much detail. But it also talks about textures of different materials classes and how they're formed. And so in that way, it's a book that's maybe a little more applicable than just the theory book that Bunga's book is. And then for EBSD specifically, there's the Electron Backscatter Diffraction in Material Science. There's 2 volumes of that. The first edition was published in 2000 and the second edition in 2009. So there's a lot of application notes in there, as well as a little bit of stuff that says how the technique works, but mostly it's application notes. And then finally, the book by Olaf Engler and Valerie Randall, which kind of covers both the mathematics and the applications. It is probably the most accessible book in this area. So it's a textbook designed for the person beginning in EBSD and texture analysis. Although it does go into some in-depth work as well, but it's designed for the person who's beginning, kind of early level graduate student. All right, so when we talk about texture analysis, we're talking about how can we take the orientation information that we measure and create distributions, create probability distributions from these. So if we take straight up what we've looked at so far, we take individual measurements. What we're showing here would be a 111 pole figure, which it's not showing on there, but it's a 111, I think I can write on this if I'm clever. This is a 111 pole figure for rolled FCC material that's being shown. And each of these individual points in a 111, there's going to be 4 of these, right, for an individual measurement. And each of those corresponds to the measurement of one single crystallite, one grain. So when we look at the distribution, we see these patterns that form. So we have what we call preferred orientations. Problem with just looking at plots like this is you don't know, you see dots here and you don't know if there's just barely enough dots that it kind of makes things black, or if there's thousands or even millions of dots in that dark point, right? So it's not quantitative. It just kind of shows us where the preferred orientations are. So the idea is to become more quantitative. So if we take something like this is showing a fiber texture, and this one again isn't labeled, but it's a 100 or 200 if you prefer to say that. 100 pole figure for probably a directionally solidified material. So the growth direction would be this direction coming out. And the only reason I know these things of what the textures are is because I know what kind of textures form with which kind of processes, right? That's one of the things we use texture analysis for, is forensics on material, to see how things were processed or see how material was flowing before it was put into service, something like this. All right, so what we are going to define now is an orientation distribution function, call it an ODF, and that's a probability density function. So we call it an orientation distribution function, but it's actually a probability density function. And it describes the probability of finding a grain that has an orientation of dg about some point g, right? So if we say, you know, we never have probabilities of individual points, so we say here in orientation space, if this is a point that we're calling G0, then we have some volume around that space that is, we're going to call that delta G, which I prefer usually to call it dG, because delta G usually means misorientation. But here we've used delta G. So see what the probability is to get an orientation with some kind of infinitesimal volume about that point, right? Now, you can't see my nice equation here, but this is just defining what the function is. So I'm going to write this equation, since we can't see it well on that. So this is effectively how much volume fraction do we have, and we're going to write that as an integral of my function f of g dg. And that is for g being a member of this G0. Okay. Now for EBSD measurements, of course, we collect the individual points and then we make some quantitative measure out of it. All right, so now let's go back to my simple thinking brain. So we're working with orientation space that's in 3 dimensions, but let's start off with a single dimension. So let's say this is orientation space, this line. And it can be the triplet of Euler angles somehow mapped onto a line, something like that. So we're measuring orientations, and so we say we measured a point at each one of these places where we have an X. And then we create bins. So we say, okay, in this bin we have 1 point, in this bin we have 0 points. This bin, 1 again, maybe there's 2 in this one, maybe there's just 1 point there. We have 3 points in this bin, right? So then we just say this is how many points we have in each of these bins. And then we want to create a function from this. So you can see how the function is being shown. And we want to make that so it's effectively representative of what our orientation distribution is, what our probability density is. So I know just looking at these types of data, assuming these are statistically reliable data, that I have, if I have a polycrystal and I put a point down anywhere within that volume, then it's the highest probability of having this orientation, right? So this orientation here is the most probable orientation, assuming I have good statistical reliability. But there's also probability that I would get some of the others. And in some cases, it's likely that I would never see those, right? These ones that are missing, maybe those don't exist in the distribution. Now we worry about how do we quantify this? So what should the bin size be? Should I make these bins bigger? Maybe I should have 5 points in that bin and 3 points in this one and 3 points in that one, right? Maybe they should be bins like that. Or maybe they should be even smaller. right? So what am I trying to represent? And then when we represent the equation that shows that distribution, do I want to do very fine features so I can basically pick out all the individual measurements, or do I want a very smooth feature? Right, so this is all the questions you ask yourself as you're coming up with the mathematics to describe textures. All right, so there's basically two strategies we use with EBSD data. Right, with X-ray data, we use completely different strategies where we measure partial pole figures, and then we'll talk about this in a future lecture, but we measure partial pole figures, we calculate an orientation distribution from that, and then we recalculate pole figures. We call it pole figure inversion. Okay? And that's because with X-ray data, we're measuring the orientation of planes. So we get two-dimensional information from our X-ray measurements. Right? We don't know what the orientation in plane is. So if there's a 111 pointing like this, we don't know where the 110s are within that plane. All we know is the 111 is pointing like that. With EBSD data, we have all the information, so we have three-dimensional data, right, when you do individual orientation measurements. So if we map our Euler space, so phi 1, phi 2, and capital phi, so if we have all of those, then we know exactly where our point is going to lie in that space. Right, so maybe our point's going to be at some specific spot. And so we can add all these things up, we can smooth it out, we normalize, that's this equation, again, you can't read. We normalize so that f of g dg over all of g is equal to 1. Is we just normalize it so that we have a distribution to look at. Yes? So the question is, what is a partial pole figure that I mentioned? And so as you're measuring with X-rays, you have a specific angle that you're measuring at. So you have theta coming in, theta coming out that you're measuring at. And you have to rotate your specimen in all directions around the polar and azimuthal angles. You can't go all the way to 90 degrees, right? So you're measuring it, you can't go all the way up, so you go to some fraction of that. Usually we go to a polar angle from 0 down to about 75 degrees. So we miss from 75 to 90 degrees on the outside of the pole figure. So that's just information that's not experimentally obtainable for us. So that's why we call them partial pole figures. If you do it inside a TEM or inside a transmission neutron beam or something like that, then you still have a problem on the center. So you get all the outside, but you don't get the center well. Okay. So this is called a binning approach. If we look in the software, this is going to be the binning approach. And this is one technique that has been, we credit it to Matisse, the paper up here, Matisse and Vanel. Sometimes we have problems because it's a nonlinear space and we're trying to look at invariant volumes of each of these cubes. We have a lot of mathematics to play with those, and we can get a pretty good estimate of what the texture should be using a binning strategy. All right, the other way, yay, my equations you can see. So that's good. Small celebrations. Okay, spherical harmonic calculation. So this is using our spherical harmonic functions. And now we're going to call these spherical harmonic functions T functions. T is a function of G, where G is the orientation. LMN are the indices, so they're the order of harmonic. And again, these are the functions that I said are just like sines or cosines, right? So if we have a triplet of Euler angles and we know LMN, then we can tell you exactly what the value of the function is. So that's the spherical harmonic functions. Now these functions, I didn't write the definition for the three-dimensional spherical harmonic functions. Sometimes they're called spherical body harmonics. So the ones we talked about last time with spherical indexing were on the surface of a sphere. This one is with all three angles. Instead of just the polar and azimuth, this one now includes all three other angles. These are complex functions. And I don't mean complicated, I mean there's a real part and an imaginary part. Right? So there's real and imaginary parts of those functions, which means our coefficients to the functions, the C functions or the C values are the coefficients. Those are also complex. And so the value for the actual orientation distribution has to be a real number, right? So we have complex functions, complex coefficients, and we get a real number out for the probability density, okay? So these are infinite, so L equals 0 up to infinity. You can't see that there, but it goes up to infinity. And then N and M we're summing from minus L up to L, right? So when this is equal to 1, we're summing minus L 0 and or minus 1, 0, and 1. All right. So this is a general definition of the orientation distribution function. So f of g we call the orientation distribution function, and this is a Fourier series expansion that gives you that distribution function. Now you know from Fourier series expansions that they're infinite in nature. They assume things are periodic, right? Even though the period might be, we just have our data over one period sometimes, but we assume the data is periodic. And we can represent these with all the various harmonic functions that we use. And however we truncate those, we never go to infinity, obviously, numerically. So we truncate those at values like 16 or 32 or 42, something like that, we'll truncate. And that will tell us how much information we get in the function, how sharp those peaks are going to be. So this strategy of how to actually do the calculation is going to help determine exactly what numbers you come out with on the function. Right? So how we calculate it helps determine what our answer is. So it'd be nice to know the answer first and then do the calculation so it matches the known. So sometimes it's good to do the binning and the harmonic functions both to try and come up with the best approximation. And we'll talk about some strategies to do these things. All right, so here's the function. Now if we use individual orientation measurements to calculate the C coefficients, it becomes a very simple procedure. So again, these spherical harmonics are known. That GI is the known orientation value, measured orientation. Okay, so it's the ith measurement. So if you take 100,000 measurements in a map, in an EBSD map, that's the ith measurement out of those 100,000. So for each one of those, we know this function, spherical harmonic function. K is a value that we determine, which we'll talk about. It's a pre-multiplier value, which we'll talk about how to use that. And then this value, 2L plus 1 over N. N is how many total measurements we have. And 2L plus 1 is a value that comes out as we're doing the analysis. So that's the value you see a lot of times when you're playing with spherical harmonic functions. So that will give us the value for the C coefficients. So we sum over, say N is 100,000 measurements. We sum over 100,000 measurements. We divide by 100,000. 2L plus 1 we've pulled out of the summation, and we get exactly the estimate of our coefficients for the Fourier series expansion. And all of these are known values. These are just numbers. We've measured that, so this plugs in. We know all those. We get these coefficients. Once we have that coefficients, we can plug that in to this equation. We go over all space, and we can determine exactly what the ODF is over all space. Okay. Everybody's still on board, so we can do binning and we can do harmonics. That's the two different ways we can calculate from EBSD data. Okay, so here's a little bit of a comparison. Generalized spherical harmonic expansion, we say it's well established, and that's because that's the technique we use to invert X-ray pole figures. So this has been done since Bunge's analysis in the mid-60s, and Rowe was another one that worked on this simultaneously in the mid-60s. And if you look at the values that are being shown here, we're saying if you have the green curve, so we're truncating at L equal 4 in the series expansion. So instead of L going to infinity, we stop at 4. We just sum L equal 1 to 4, or 0 to 4. Then we get this green curve that represents the distribution. So a very smooth type of a representation. Whereas if we go to a higher L equal 34 distribution, then we get the yellow line. All right, so comparing that with binning, say here that we have artifacts in binning. And one of the reasons for that is that we have bins that we set up. So let me just draw a bin. And let's say this is, 5 degrees, and this is 10 degrees something. And we're doing it in 3 dimensions, so it's actually a cube that we're playing with. But let's say the measurement happened at 5.1 degrees, and so we're right there is where the measurement happened. And we put it in this bin. Now maybe, our measurement certainty or measurement resolution is to within half a degree or maybe 1 degree. So actually that measurement maybe was anywhere in here. So it might have belonged to this bin, or it might have belonged to some bins down here. So what we will typically do is around each point, we'll say, well, instead of saying that is a delta function, a specific point that happens only at 5.1, let's give a little bit of love to everybody around it, right? So instead of in 1 dimension, we would say there's the bin, and instead of just having a point there, let's do a little Gaussian curve around that. And we're going to give a little bit of orientation intensity everywhere here. Right? So this is the Gaussian. Now the width of that Gaussian peak is going to determine how smooth our data is or how sharp the data is. Right? So we're going to put some kind of value for the Gaussian in there. If we have a whole lot of data, we probably don't need to do very wide Gaussian peak. If we have less data, then we need to put a little wider Gaussian peak typically. Or if we have a really strong texture, then we don't want a very wide peak because then we can't calculate a strong texture. But we don't know we have a strong texture until we measure, right? Okay. So larger bins, of course, will give you more of a smooth curve, like the green one. Smaller bins will give you more like the orange curve. And then we're saying which one's correct, so depends exactly what you're looking at. If you're looking at something like elastic anisotropy, which somebody mentioned, we talked about earlier. If we're talking about elastic anisotropy, that really only depends on the L equal 4 coefficients. So we can describe the elastic anisotropy of your material if we only calculate the ODF to L equal 4, right? Because the other terms don't play a role in elastic anisotropy of the material. But that's going to be different depending on each different property that you're looking at. So piezoelectricity is another one we talk about, 9th order. Plasticity is more generally, we can go to very high order and still get additional information for plastic deformation. Okay, so if we take our pole figure here, these are the individual discrete measurements for this one that we've looked at. We calculate the C coefficients based on these. We plug them in here. Then if we go to L equals 16, so that's this value we've truncated, right? We're showing 16, 22, or 34. So if we truncate at 16, here's the calculated pole figure that we get that represents this data. Right, so you can see it's, and I don't know if you can see my pen here, but this one here. And you can smooth, you know, these peaks within here are much smoother than if you look at the one down here for L equal 34. Right, so these peaks in here are sharper, more distinct. These are more smoothed out, which you expect from higher order expansion in Fourier series. So which one represents our data better? This one's showing relatively few measurements, it looks like. In my mind, it looks like, because we have, you know, maybe this should have an orthotropic symmetry, so this point should be equivalent to this point, should be equivalent to that point, to this one, right? They should all be relatively equivalent. So it looks like maybe we don't have enough data for this. So I don't think I can trust anything like this. I think I would trust this one better. Up here with the L equals 16, I think I would trust that. But if we have more data, then maybe I would trust this one better, right, for the L equals 34. So these are determinations you have to make as you're doing the calculation. So these are all user parameters in the software where you go in and say, I'm going to truncate at this specific value, or I'm going to use this bin size, or I'm going to use this Gaussian smoothing. Okay, so here's a little discussion on Gaussian half-width. This is the parameter we're looking at, this k value that's used in determining the coefficients of the Fourier series expansion. And this is an equation that gives k here, where omega is the half-width of the Gaussian spread. Right, so if the half-width of the Gaussian spread 5 degrees, that means you come down to the half of the full maximum position. Half of that peak is going to be 5 degrees, so the full is going to be 10 degrees across that. So if we're looking at the same data and we go to L equals 8, that's what this says here, L equals 8 or 16 or 32, we use a half-width that's very narrow versus a half-width that's rather generous. A little bit of difference, not too much difference that you see. So maybe, you know, maybe for this one that's going to be fine to use the very small half-width. This half-width, as it gets bigger, just introduces artificial smoothing in the data. And you see some features, obviously, that you'll see up here at the very small width, where some other little features are included that you don't see down in the larger one. And maybe you want to avoid those, and maybe you want to see them in your distribution. Right? Depending on what you believe is true on your data. All right, so if we look at this now, this is an equation that's used as a guideline. And n is the number of grains that you're looking at. So it's not the number of measurements now, it's the number of individual grains that you're looking at. And p is a function, is a number that says this is how strong the texture is. So it can be 0 if we have a random material, 1 for a single crystal, so 1 if it's a very sharp texture, down to 0. So we can use a value like this or an equation like this to try and guess what omega is going to be. But in general, it's best to just grab a lot of different crystals, a lot of different grains, and make omega small. So what this says at the end that you can't read, simply choosing omega equals to 0.1. Does the job, as long as we have a lot of grains. Which if we don't have a lot of grains, then we have problems with statistical reliability anyway, right? So getting more data is important. And then this is just showing a demonstration of what we're looking at. So this is an X-ray determined pole figure compared to what we get if we have 134,000 different grains versus down here in the bottom one where we have 118 different grains. Okay. and then just showing the strength of what P would be versus what omega would end up being if we use this equation. And if we have a lot of grains here, you can see that just stays really flat. Right? So it's always best just to get a lot of grains. Okay, sample symmetry. In the old days with X-rays, we always assumed sample symmetry. A lot of times, we would, if we showed pole figures, we would just show 1/4 of the pole figure. Right? It wouldn't be an inverse pole figure, it'd be a pole figure, but we're just showing 1/4 of it because it's all symmetric in the other quarters, so it doesn't matter. What we believe, since we're doing individual orientation measurements, is if we can avoid using sample symmetry, we should avoid using it. If we have enough orientation measurements, then let's not assume an additional symmetry. And let's just get enough data that we can represent the function well. And the reason for that is it's usually, well, it's never completely symmetric, right? Because the processing is never going to give you the exact results. We're going to have difference on the top row versus what we have on the bottom row if we're making a sheet, for example. Or if we're doing some kind of extrusion, we have little different micro features on one side of the die than we do on the other side of the die. Right? So there's always going to be some difference. So if we can collect enough data, let's just not include sample symmetry. If we include it, we actually save a little bit of time as far as calculations. We can calculate the functions easier, and we map everything onto that one quadrant, and so everything's perfectly symmetric, right? In this pole figure here, perfectly symmetric. Yeah, that would be the rolled sheet. That would be orthotropic, right? Right, so there's four elements of that symmetry group, right? So we can go 180 degrees this way, or this way, or this way. Okay. These are twofold symmetry, right? So plus rolling direction equals minus rolling direction, right? Or plus TD equals minus TD. Yes. All right, so here's a egregious example of using sample symmetry wrong. So if we have a extruded wire or a drawn wire that has in this case, has a nice 111 fiber texture coming straight through. On this one, we're not enforcing any sample symmetry. On this one, we are enforcing sample symmetry, so everything is axially symmetric. Right, so that means if we have a point in the center and then 3 points on the outside, which you would get for a 111, then those 3 points would be equally probable anywhere around this circle. So we put them in anywhere around this circle. So that means when we plot this bottom one with symmetry enforced, everything, any point along that fiber has uniform probability. We've forced that to happen. Okay? So now we're taking the same texture and we're measuring it from a different point of view. We're measuring it from the cross section. So the texture, if we don't rotate it to make it look like this, the texture is now going to look like this, right? Because normal to the direction now is going to be a radial direction, and the 111 is going to be along some, in this case, it's going to be a reference direction, right? That's our reference direction. So then we get this, and if we say, well, this is a drawn wire, so we're going to enforce axial symmetry, and we do it wrong, so we're not in this coordinate frame here, we're in this coordinate frame, then all of a sudden this point that's out here that's so strong is going to be uniformly the same all the way around. So then we get this one that's there, which is just the wrong texture, right? That's not, that implies some kind of fiber texture that doesn't exist. So that's what this example is showing. Yes? So fiber texture is when we have a specific direction aligned with a known direction in the sample, and then there's uniform probability within the plane of all the other orientations. So if we have 111 normal to the sample like this, then all the other 111s will be uniformly probable anywhere around that 111 axis pointing straight up. That's a simple way to think about fiber texture. And in processing materials, we get a lot of fiber textures. Okay, another question. So in this case, it's axial symmetry. Orthotropic is the one with 4 symmetry elements that we talked about.
So because the cross-section has the 4 symmetry.
This one does not have the 4 symmetry. It would have symmetry. So you're saying we should enforce orthotropic symmetry on this. So we could have plus or minus drawing direction, plus or minus radial direction. Yeah, maybe. Maybe that would work. Right, and then we would just look at this quadrant and we would get the full information. So maybe we could enforce another orthotropic symmetry, yeah. From that plane, we do have that.
Because it is in cross-section, it's radial influence of the radius is not coming. With the wire, even with the wire, on the measurement, the influence of the radius is coming.
Yeah, if we're not assuming any kind of gradients through there, which are going to probably exist, we could maybe assume a orthotropic symmetry. But again, this is where we say if possible, let's not enforce a sample symmetry. Let's take the raw data and let it tell us whether it's actually symmetric or not. This is just an egregious example of saying don't enforce sample symmetry wrong. But I would say don't enforce sample symmetry at all if you can help it. Okay. So sampling strategy. So let's say we want to measure texture on this pipe. And the pipe has been extruded, let's say. We have an extruded pipe. And probably we're going to have some specific orientation that is aligned with the radial direction. So it will be aligned like that, it will be aligned like this, it will be aligned like this. Right? So it's going to be normal to that tangent everywhere, whatever texture we have. And in this case, we have these 100 directions that are growing radially like that. If we sample on a plane that's being shown in pink here, sample on this plane, then we look at across that plane what the orientation distribution will be. Since the radial direction in the middle is poking straight up, the radial direction in this side is poking out. This one's poking out. It's going to make it look like we have a nice spread of orientations. Whereas in reality, we just haven't sampled very well. Right? So we're not looking at a place where it's going to show us what the nice strong 100 oriented with the radial direction is going to be. Now we can back that out once we know this, but it's very difficult if we have a point-to-point difference in what the actual texture is going to be. So it'd be easier to measure that along this direction, cut the plane like this, and then measure this plane. And then we would have a texture that we would have like this, instead of this diffuse texture that's being shown from this plane. Right? Yes, question.
Sir, actually, if we have a directionally solidified sample,
Yes.
so similar like this, like that. So if we are taking the texture from the top, will it be like this wire, or it will be?
So question is on directionally solidified sampling. You just mean a sample that had a chill plate, and then we had a bunch of orientations, and then you get columnar growth coming up, right? This is my drawing of a directionally solidified sample. You get all these columnar grains. Okay, so these are all growing in this direction. So you see that. So if you section like this on the top, where you look at equiax grains here on the top, then you'll see something like this one immediately, right? If you section from a cross section that contains the fiber direct or the growth direction, then we would get a pole figure that looks more like this, right? So to get a diffuse looking pole figure, I don't see exactly a parallel with the one that's radial direction, because even if we sampled at an angle, we would still have a sharp peak in our fiber. It wouldn't be diffuse like we would see from this plane here, right? We'd still get a sharp peak. It would just be oriented in a direction we didn't expect.
One more question.
Yes, another question.
In case of directional solidification,
Mhm.
we will usually encounter with the enlarged grains. So we will have a large grain size.
Right.
So it will be easier for texture analysis to do it in the XRD better than the EBSD, because we have to take a large area for that. So this slide size will be longer as compared to the normal sample.
Right.
What do you suggest?
Right, so the question is, what happens if you have a large grain size and directionally solidified material is specifically referenced? If you have a really large grain size and you're trying to get enough grains to get a texture measurement. So if you're doing EBSD data, then probably you're going to have to take a bunch of different fields of view, right? So you're going to have to take 10 scans in different places, merge them all together to get enough data to have a reliable texture. So XRD is obviously an option anyway, right? That you could do XRD measurements, and either one would work. Either one would work fine. So you just have to take several fields of view to make sure you get enough information, right? So if you're scanning 2 centimeters by 2 centimeters in XRD, and you want to cover that same area with EBSD, I don't know what your system's set up at, but my system can do maybe 1 millimeter by 3 millimeters is about the biggest area I can look at. So if I'm going to do 2 centimeters by 2 centimeters, I'd probably have to take 100 scans, right, to get the same data. But they would probably be very quick scans because I'm not going to have a small step size. So it could be done. And there are, in the data collection setup, you can move the stage. So you can take an area, move the stage, take an area, move the stage, take an area, and so you can set that up so it does it automatically, so you don't have to sit there and click the button each time. Okay, sampling. Okay. So I've talked generally about binning, and I've talked about generalized spherical harmonic functions. We talked about how to get the coefficients using the generalized spherical harmonic, where you measure the orientation, and then you just plug in directly into what's known to be the generalized spherical harmonic, or what's known to be the spherical harmonic function for that specific orientation. You average all those and you get all your averaged coefficients. Or to do the binning procedure, which you have to smooth and do some of these kind of functions. Now there's additional functions that we measure, usually based on misorientation distribution, that's the MDF. Instead of ODF, where we say orientation distribution function, we say misorientation distribution. And that's for looking at grain boundary structure or relative orientations. So there's a lot of ways to do these, a lot of different functions to look at. So I'm going to show you a few studies and a few calculations, and we'll just look at generally how this is done, or what people do. All right, so orientation distribution function. Sometimes we call that the 1-point function. And that says if I drop a point anywhere in the material, what's the probability density for having an orientation of delta G about G naught? Right? What's the probability density for having that specific orientation? If I look at the misorientation distribution function, I'm looking specifically at neighboring grain orientations. So if I have GA, I have GC, delta GAC is between them, right? So I have to measure spatially specific information and then say I can calculate this function exactly the same way. We're still using Euler angles for the relative orientation or the misorientation. And we can still do the exact same kind of a function. That f of delta G can still be done the same way with the triple summation of some C coefficients, but now I'll call them maybe a D coefficient, LMN, and then T LMN of delta G. And we can use that delta G I specifically to find out what the D coefficients are. Right? So I'm not going to write that whole equation, but you can get the coefficients for that function in exactly the same way as you do for the orientation distribution. These are, just consider these to be a polar and an azimuthal angle and a rotation about that axis. So it's an axis angle description of misorientation. Mm-hmm. So delta G in this case is being defined by these angles. It could easily be defined by these same Euler angles, right? Just doing it to differentiate from the nomenclature we use up here. All right, we can get more complicated than that if we want. We can say, well, we know a grain boundary has a grain boundary plane involved, which I'm going to talk about here in a minute. But that grain boundary plane also has two orientations. It's a unit vector that describes the orientation of that plane. So the plane, each one of these planes, can have a polar and an azimuth associated with it as well. So now all of a sudden, instead of 3 dimensions, we have 5 dimensions in the function. Right? And with those 5 dimensions, we can just add that information into here. Right? So if I want to do this function, and I'll just write this one just for fun, although I do write it later, I have it printed. So this is n. Then I can say that's going to be a summation, but now we have 5 signs. And then we'll have some kind of coefficients. And now it's L, M, N, O, P. Right? We have five coefficients, or we have 5 indices on our coefficient. And then we have T, LMN, delta G, and then we multiply that by this y function we used earlier, that now we're using a chi and an eta for the angles. And I used an O and a P coefficient for those. Okay. So those can be done in the same way, expand them in a Fourier series expansion. Now I have a body harmonic and a surface harmonic that's included in the Fourier series expansion. It gets ugly, it gets to where it looks complicated, but it's just bookkeeping, right? These are the coefficients I need, so these are the ones I'm going to represent. This one is even worse. Now I have 8 parameters. Or 9 parameters, depending on how I want to do it. And this is a 2-point correlation. And so what we're saying now is instead of dropping a point anywhere, we're going to take a vector. And we're going to drop that vector down into our polycrystal. We'll say, what's the probability density of having G at the tail of the vector and G1 at the head of the vector as a function of what the vector is. right? So the vector can go through all space. So we call that an orientation coherence, which maybe we're going to have a band of 111 orientations and then a band of 100 orientations, and all that information can be held in a function like this. So we can get complicated if we want, but we can still use the same mathematics to represent all of that. All right, so this is sometimes the misorientation distribution we refer to as grain boundary texture. And the grain boundary texture has 3 values. This is the angle of rotation, and then the axis and or the polar and azimuth that defines the axis. So we're plotting constant omegas on this. So this is omega 0, omega 5 degrees up to 65. So if we do cubic crystals, then 62.8 is our maximum rotation angle, right? So going up to 65 is adequate. We are plotting what the orientation or what the grain boundary texture is as a function of these parameters. So if we come here and we say at 60 degrees, we have a lot of 60 degree 111 boundaries. And if you're working with FCC, you say that's an annealing twin, right? So this, if we're looking at copper or nickel, something like that, with moderate to low stacking fault energy, we almost always get some kind of distribution like this, where we have a lot of 60 degree 111s. Now, 60 degree rotation about a 111 axis is exactly the same as, or is symmetrically equivalent to a 70.5 degree rotation about a 110 axis. And so this big peak that's coming in down here at 65 degrees from 110, that's just the symmetrically equivalent twin. So when we plot this entire space, if we go up to 45, we're fine, but once we go higher than that, if we're looking at only a fundamental region, we really should crop out this. So this part wouldn't exist, and then this part wouldn't exist, and then this part wouldn't exist, and up here only the very top piece exists. If we're talking about a fundamental region, which means there's one symmetrically indistinguishable point for each possible misorientation. All right, so this is in 3 dimensions where the misorientation lies, but a lot of times we describe a misorientation just by the angle itself, right? So this is the same information as what's being plotted here, except we're ignoring alpha and beta. So then we just plot the misorientation angle histogram, and you can see you have a large peak here at 60 degrees. And so you might assume, okay, that's a bunch of twin boundaries, but you don't really know if it's 111 60 degrees or if it's a little bit off 111, right? So you have less information, but it's maybe easier to represent. Can I tell from this function if these are coherent twin boundaries or not? Coherent twin boundaries means you have the plane along 111. You can't tell, right? I saw a few of you shake your heads a little bit. You can't tell because you don't have any plane information in these functions, right? So this one we have only misorientation angle. This one we have misorientation and axis. Could we include the plane? Yeah, we could. We can calculate that and include that in the distribution. And there's buttons in your software that lets you do that, and it's useful to do sometimes depending what you're looking at specifically. So there's ways to do that, which we're going to talk about here in a minute. Yes. Okay, omega is the axis of rotation, or the angle of rotation. So it's the misorientation angle, right? And that's an omega. I know how to draw an omega. And alpha and beta are the axis. They're polar and azimuth.
is like this and you are rotating like this.
You're not rotating your sample, you're rotating the crystal lattices that are in one grain versus in the neighboring grain. Right? So how much do you have to rotate one of the crystallites to be in coincidence with your neighboring crystallite? So if we come back here, that's this delta G that we're talking about. So how much do we have to rotate G sub C to be in coincidence with GA? Okay.
Twins are in general not coherent. Can be non-coherent also.
I didn't understand.
Twins generally found like in FCC crystal. The annealing twins, there is a mirror plane symmetry in the twin. So mirror plane, since there is a mirror plane, so it's not coherent.
Right, so we define those by a rotation axis. Right, so a 111 rotation about, or a 60-degree rotation about 111. So a twin is actually, you can think of it as a mirror, but you can also think of it as cutting it, rotating at 180 degrees and putting it back together, right? So a twin is defined by a 180-degree rotation. And so for the FCC twin, we say it's a 60-degree rotation about 111. But that's because 111 has a threefold symmetry. So we go to 120 degrees, it's just like starting at 0. So we go another 60 degrees to get to 180, so then we just say it's 60-degree rotation. Okay.
So the angles shown here like 0 degree, 5 degree, they are the omega values.
Right, so that is so these are low angle boundaries going about all of the different axes, right? And once you get to high angle boundaries, then you can distinguish a little bit better which axis it's going about, right? Okay, so should we take 5 minutes? It's 1 hour, 1 hour's up, so you want me to finish at 11, right? So let's take 5 minutes, take a break, and we'll give these guys a break, and then we'll come back and continue with this. We'll start on this one.
So today there is an attendance, okay? So I am going to take an attendance. It will be very easy.
You should have announced that yesterday. So are we running again? We're ready? We're going? We're live, okay. Okay, so we'll continue. So SPARC is a program. We have to write a proposal for the SPARC award that we got, which allows us to come here and offer this workshop. And the proposal that we wrote is focused on looking at triple junctions. So the character of triple junctions. And specifically because as you go to nanocrystalline materials, then the volume of triple line becomes a significant fraction of the volume of the material. So studying grain boundaries and triple junctions is an important part of the work. So that's the software that you use has a lot of tools for grain boundaries. So I'm going to talk about some of these grain boundary tools, and hopefully we can extend a lot of these into some triple junctions, to how to study triple junctions. So that kind of sets the foundation for why I'm going to talk about grain boundaries here a little bit. So when you talk about boundaries and you hear about people working on grain boundaries, there's a field of research called grain boundary engineering, where you get a specific, you're focused on getting a specific type of grain boundary or excluding a certain type of grain boundary from your system to improve the properties of your material. So people use this term special, and I put in quotations, right? Special boundaries. And they've used a number of different criteria to define that. Some just based on misorientation angle, as you can see here. Draw my laser pointer to begin with. Misorientation angle. So if you look at the Reed-Shockley model for grain boundaries, low angle boundaries are low energy, high angle boundaries are high energy. And so just misorientation angle, right? We just distinguish between low angle and high angle grain boundaries. Second is this coincident site lattice boundary. And I'll have a slide that describes that, but basically we're saying if you have a long range, if you extend your crystals into one another from the various grains, there will be a certain number of lattice sites that are in coincident sites. And the higher fraction of those coincident positions you have, then the lower the energy of the boundary will be. Because that means atoms on a specific boundary will belong to grains in either lattice. They'll be in the right position for grains in either lattice. So we'll talk about that a little bit. Group multiplicity greater than 1, this means symmetric type of boundaries. And then just symmetric boundaries in general that have a low index plane lying along the interface. So all of these are used in literature to define special boundaries. Now, a lot of times when we use these types of criteria, we presuppose a specialness criteria. So we'll say these boundaries are low energy, these boundaries are low diffusivity. If I have a crack going through the material or stress corrosion cracking, something like this, I expect this boundary to crack and I expect this boundary not to crack. But how can we analyze material and just determine from the data which boundaries are special, which boundaries will crack or which boundaries won't crack, for example, or which boundaries have a lot of second phase growth and which boundaries don't. All right, so here's that little sketch I was telling you about that shows a grain boundary plane. So if we want to look at the geometry of a grain boundary, we have a orientation GA that's defined in the reference frame of the sample or some kind of external reference frame. And we can also define GB. So we have also a boundary normal orientation. So this is supposed to describe a segment of a boundary that has a unit normal in this direction. So then we have these parameters, which is 3 parameters for GA, 3 parameters for GB, 2 parameters for N. That gives us 8 parameters now to describe a boundary. Or we can ignore an external reference frame, so just take this out and look at the misorientation between these two. And then we take it down to just a delta G, right? So then we have delta G and N, and we have 5 parameters. So typically if you listen to grain boundary people, they'll say a grain boundary lies in 5-dimensional space. And that's what they're talking about, this misorientation between 2 neighboring crystallites and then the orientation of the boundary plane. So that's 5 parameters. But if we have any kind of external force, if we're deforming this based on, you know, some tensile axis defined by our reference frame, then we can't ignore the reference frame, and then we have to use 8 parameters to describe the boundary. All right, so somebody was asking me about the mathematics for a misorientation just before break. So here it is. This is the misorientation. This is the GA and the GB transpose. These L parameters, remember, these are the symmetry elements for the crystal symmetry. So they're the left-handed symmetry elements. So here we have this left-handed symmetry element on the right-handed side. Does that screw us up? That's because it's transpose, right? It's GB transpose, and so then we flip that symmetry element to the other side, right? So ignoring the symmetry elements, we just have GE times GB transpose. That gives us the misorientation. And then the misorientation angle, of course, is defined just by the elements along the trace. So the 1, 1, 2, 2, and 3, 3 components of this delta G matrix, that's what the trace is, the sum, right? So if we were to write this, in terms of Einstein notation or repeated index notation like Sinish is using in his lectures, we would say the trace of delta G equals delta G II. So it's the sum of 1, 1 plus 2, 2 plus 3, 3, right? Okay. So the misorientation angle, which we called omega previously, right? We were calling that omega, is just dependent on the trace of the matrix. The non-diagonal components in delta G will give you the axis of rotation. Okay. All right. So we're describing this boundary. 5 parameters we talked about, assuming that we ignore the external reference frame. 3 for the misorientation, and 2 for the boundary plane itself. And the 3 angles, we can use Euler angles, we can use an axis and an angle, we can use Rodriguez vector, however you want to parameterize it. You can use a quaternion, which is also 3 parameters that's put into 4. And then I showed this before under orientations, but just to remind us of the relationship between all of these different parameterizations. And we can do mathematics in any of these space. Typically, we're going to focus on Bunge Euler angles because we're using the spherical harmonic functions, and that's what is used as basis arguments in those functions. All right, so we have a nice orientation map here on the top, and you can see a number of boundaries. You can see a scratch in the sample. That's not good, but you can go in and do analysis of these types of boundaries. Now the problem is, if we look at any of these boundaries, well, most of these boundaries, these twin boundaries, they're pretty much nice and sharp, although they do have steps on them. From time to time, you'll see a step on a twin boundary. But most of these boundaries aren't nice, sharp planes, right? They're curved surfaces. Thank you. So we have these curved surfaces of our planes. So when we talk about 5 parameters that describe a grain boundary, we're not usually talking about the entire boundary. We're talking about an infinitesimal segment of that boundary that has those specific properties. And then as we do the entire distribution, then we get the overall feeling of how much would be in each different orientation, right? You can see a lot of these boundaries, you know, very, very curved type surfaces on these boundaries, which is what you expect. If we look at a deformed structure, the boundary is not even very well defined, right? With optical microscopy, where you etch a sample, you put it in the optical microscope, you look at it, and you say, okay, there's my boundaries. Those are defined by whatever your chemical etch does to the surface of the specimen. In EBSD, you have to go in and tell it, this is what I define as a boundary. Right? You have to say, this is the misorientation that's defined as a boundary. And sometimes you'll get, you know, regions like this where they say, okay, that's a boundary there, that meets your 5-degree criterion. And all of a sudden it doesn't meet your 5-degree criterion anymore. So your boundary stops in the middle of your grain, right? Which doesn't really happen intuitively, that wouldn't happen, but as far as the way we define a grain boundary using EBSD data, then that could potentially happen, right? So we just have to either accept that that's the way we define the grains, or we have to modify our definition so we don't see that. All right, so how do we measure boundary plane normal orientation? Usually we're looking at a section plane, and we only get two-dimensional. We see the trace of the grain boundary, but when you see that trace, you know, you see a line on your boundary. The boundary could be, you know, 180 degrees anywhere that lines up with that trace that we see on the surface. If we have three-dimensional data like is being shown here, where we've done serial sections, reconstructed the volume, then you can pull out a grain, pull out a nice grain, and you know exactly in 3 dimensions what your boundary is. So we do that if we have a dual beam microscope, right? We can do that. It takes a lot of analysis time. The EBSD is relatively quick compared to the focused ion beam sectioning down, especially sectioning down to where the surface is still good enough to get EBSD data. Right? So it takes a long time to do the fib. So if we look at a volume in a standard fib, if we look at a volume that's about 100 micron cube, 100 microns on the side of a cube, that will take about 72 hours to map up a structure like that. Right? Just takes a long time to fib away all the material. There's an instrument called a plasma fib now, which I haven't used, but I'm excited to use one someday, where you get relatively clean surface and you're fibbing at a much higher rate. So instead of doing a 100 micron cube, you could probably do a 1 millimeter cube in that same 72 hours, that same 3-day period. Okay. So we're looking at this N, and we can measure them independently. You can measure them exactly. We can look at EBSD or some kind of microscopy along one surface and then along an adjoining surface. And so then we get a trace of a boundary here, and we get a trace of a boundary there, and we say, okay, that's what the boundary is on that corner. So then corners would give us the full information. So we could get that N of the specific boundary. Now the function we actually want is S sub V times N. Now this S sub V is different than what you were shown in continuum mechanics, right? In this case, this is a stereology measure, and that means surface area per unit volume. S sub V, surface area per unit volume that has an interface with the normal N. Okay, so how much surface area per unit volume do we have in that direction? And we can pull that out from plane sections, which is kind of cool. Can do that either measuring points along a line or measuring angles on the plane. So let me just show you quickly how that works. So we have this is points per unit length, right? So that means intersections of a grain boundary plane that we see on a surface. So there's our grain boundary plane. There's the normal to the plane. So we see points, that intersection, that's a point per unit length of scan line. So T is the direction of my scan line. And then if we look at the stereological equation for that, T dot N is the projection of these two on each other, right? So we get the most information if T is aligned directly with N. We get less information if it's normal to N. So surface area per unit volume, this is the function we want to measure, right? That's what we want. We want surface area per unit volume that has a plane normal in the n direction. What we measure actually is P sub L in a scan direction T. But then this is just an equation. If we can solve this equation for S sub V, then we can determine from our plane section what surface area per unit volume with a specific normal orientation. We can measure that function, right? And it turns out we can do that. Hilliard in 1963 has a very nice paper showing exactly how to do that. So we know how to do that. If we take instead this function, this is line length per unit area that has a given omega orientation. Now, unfortunately, I've reused the omega. This omega is the angle of the trace of the plane. So this is showing you the grain boundary trace. That's this line here. There's the plane underneath that you don't know what its orientation is, but it's going to have a unit normal n. And what that n can be defined by is nu and omega. So this is just n. So that's S sub v n. This is what we're measuring on the pth section. So it's a section defined by a normal p. Pth section. We use this fundamental equation of stereology now, and we can pull out, so this was published in 1986, we can pull out directly this parameter that we need from a plane section. So two different techniques we can use. Now, if we are looking at, instead of a global coordinate frame, we're looking at the coordinate frame defined by each of the crystallites, then we're looking for this delta G, and we're looking for n defined in the crystal orientation frame. Right? Is my grain boundary lined up with a 1-1-1 plane or a 2-1-1 plane or a 1-2-3 plane? With the other stereology, we're talking about in your specimen coordinate frame. Is it lined up with the tensile axis? Is it lined up with some kind of extrusion direction? Right? But in this case, n is being shown in the crystal frame. So we can pull this out directly. And so each of these has an individual crystal frame associated with it. We measure the misorientation. And then we can plot back up. This is a paper from 2004. And this is showing, this is supposed to be delta G. That's the misorientation. Times n in the crystal frame. So it's exactly this function we're looking for. And now we fixed delta G. So this is for delta G fixed. And we've said, where's the orientation of the crystal of the grain boundary plane for all the crystallites that have this misorientation delta G? And then if you plot that up, you plot it, it's a unit vector orientation that you're plotting. You plot that up over the sphere, you can see in this direction, which you can't see my pen in that red area. I could probably change the color of my ink, but that's too fancy for me, so I'm just going to leave it. So this is at a 1-1-1 position of the crystallite. You can see that. But now we're defining, instead of having all the symmetrically equivalent 1-1-1s, we're just defining that crystallite with respect to which axis is shared between the two, which of those planes is lined up there. And so this shows that specific 1-1-1 plane that's lined up, the way we've defined it. And so this plot is showing how many unit normals are lined up with which crystallographic direction anytime we have a misorientation of delta G. Now, to do this kind of stereology requires even more measurements than doing texture, right? So we said with the texture measurements where you take a single point, we need to measure 1,000 to 10,000 grains, something like that, to get a reasonable texture. With this, we say 100,000. We need 100,000 different grain boundaries to be able to get modest statistical reliability. Okay, so we described the boundary a lot of ways. Of course, we have different ways to include this. So multi-phase materials will have different different phases on each side that we'll have to consider. This is just the same as I said before. We could have a reference one way or the other. But then we look at these phase boundaries, and we can look specifically where is a beta FCC phase versus an alpha hexagonal phase. This is in cobalt. So cobalt has an allotropic phase transformation from FCC to hexagonal. And you can come in and you can look. If you look at two different patterns here, so this is a hexagonal phase being shown here. This is a cubic phase being shown here. And you can see you have some alignment with the phases, right? You can see that busy pole there is the same as that busy pole there. This happens to be a 111 in FCC, happens to be your C-axis or your basal plane pole in your hexagonal crystal. And if you look at the pole figures, there's the 111 that lines up with that one. Here's 111 lines up with that one, right? So this is the basal plane pole figure. Okay, coincident site lattice. I brought this up a little bit. So the coincident site lattice, you take two interpenetrating lattices and a certain fraction of those points, in this case it's these points, you can see I'm circling them here, are going to be in the same position whether they're in this lattice, the yellow lattice, or this pink lattice. So they're in the same position. This one we would call a sigma 5, and that's because the volume of the unit cell for the coincident site lattice, so that's this unit cell, right? The coincident site lattice cell is 5 times the volume of the primitive lattice unit cell, right? So we call that a sigma 5. Sigma 17, you can see the coincident site positions here, right? So this volume is 17 times larger than this primitive unit cell volume out here. And I'm drawing it on a plane, but it's in 3 dimensions, right? We're actually talking about volumes and not points in a plane.
The volume at the interface.
Say again?
The volume at the interface.
This is the volume of the coincident site cell, and so it's in 3 dimensions. It's not just along a plane. Now, if these points are coincident along the plane, then it's a special type of a boundary, right? We call that along the coherent plane or the twinning plane. Okay, so then that gives you an additional criterion. But for CSL boundaries, we're only looking at misorientation. So these are defined specifically by the misorientation. The FCC annealing twin, 60 degrees about 111, is a sigma 3 boundary. Right? Every third lattice point effectively is in common.
So what does the A mean? Sigma 5 A, sigma 5 B?
Sometimes for a specific volume, you'll have different variants. So they include the A. If you have different variants, you'll have an A, B, C, right? Maybe if I have 3 different sigma 5s, then they would be defined by different misorientations. So the A is just indicating one of the variants. In the case of sigma 5 for cubic, there's only one, so you could just call it a sigma 5. Okay. All right, so here's a whole mess of parameterizations. Yes, sir.
You mentioned the cobalt has allotropic phase transformation.
Right.
What does allotropic mean?
So question is, cobalt has an allotropic phase transformation, so what does allotropic mean? So allotropic, the way I'm using it, means there's no change in chemistry, it's just a temperature change for the same composition, and it gives you a different phase. So iron has that, titanium has that,
So,
zirc, hafnium.
when we say martensitic phase transformation, that's something that involves shear, right?
Martensitic means diffusionless. So it means all the near neighbors remain near neighbors. Right.
But allotropic may include diffusion.
May include diffusion, yes. Yes. Okay.
Sir,
Yes.
sir,
how this CSL boundary affect the grain size? Like in microstructure, there is a grain heterogeneous grain size. Can we explain the bimodality nature of grains with help of CSL boundary?
Okay, so the question is, do CSL boundaries affect grain size in a material? And that's actually a really nice scientific question. And the answer will be maybe in some cases. And the reason is certain CSL boundaries are going to either have high mobility, right? So they're going to move quickly, high energy, or they're going to have low energy, so they're going to be more stable. So in some cases, it's possible that certain types of boundaries will change the distribution of grain size based on the character of the boundary itself.
For example, sir, sigma 3 is a, like, it doesn't affect the grain mobility. Like it has very low grain mobility.
Okay, so the follow-up question is saying sigma 3 has low mobility, it's a low energy boundary. Now that is not actually completely true. Sigma 3, if the grain boundary plane is along that 111 plane, like a coherent twin boundary, then that's true. But if you have a sigma 3 boundary which is not defined by the plane, it's only defined by the misorientation. If you have an incoherent plane, like a 211 plane, then that's a very high energy boundary, probably more high energy than a random boundary. And so those boundaries are going to become very mobile, right? So for some of these considerations, we have to include the boundary plane information. CSL by itself doesn't include all of the information.
What are the other reasons that you can explain the grain mobility?
What are the other reasons that explain
Heterogeneous grain size.
a heterogeneous grain size? So that is a great topic that there's a conference series that discusses these kind of things, right? Recrystallization and grain growth is a meeting that happens every 3 years. Happened last year in Denmark. And there's people that discuss these kind of problems all the time. Now, a simple answer would be particles that go to grain boundaries of a specific type, right? Particle pinning causes abnormal grain growth in a lot of cases. So that could be one of the simple answers. But grain boundary character is going to affect where those particles go also. So grain boundaries do play a role. Okay.
The other question is that why the micro hardness of the smaller grain is higher than that of
Okay, so the question this time is micro hardness of smaller grains and why they would be higher than coarser grains. So micro hardness, maybe you're talking about Vickers, right? So Vickers hardness. So typically if you have very small grains, your Vickers will be include several grains, right? So you're going over several grains.
living grains. We are talking about one grain.
So talking about within a single grain. So the answer could be a lot of things, right? Maybe you're having distortion near boundaries and you have a lot more of that volume in small grains than you do in large grains. There's a lot of answers for why you would have that type of character, and it might be because of grain boundaries and it might not. Okay.
Grain boundary can be considered harder or weaker than the one.
So question is, grain boundaries, should they be considered as harder or weaker than the bulk? So typically, if you're doing hardness measurements on a material that you've had some deformation on, a lot of times you'll get some excess dislocation content near the grain boundaries, which will make them harder. In some cases, you will end up with free volume at the grain boundaries that allows a nano indentation to be a little bit softer at the grain boundary. And sometimes you'll get, he wants to expand based on his modeling. Just a second. Sometimes you'll have one side of the boundary that looks harder and one side that looks softer than the average. So there's all kinds of things that can happen. But and it's a condition of the boundary character and where the solutes go and where the dislocations end up. Yes. Okay. Comment.
The comment about previous question about why smaller grains are harder. Even if you're sampling single grain, right? You're talking plasticity. So your nuclear dislocation, you create a source, and they start moving away to their plastic deformation. But if you have a small grain, those dislocations hit the boundary, and they stop there, and they exert the back stress on any new dislocation.
Mm.
So it becomes harder and harder to move dislocations. So if the grain is small, those piled up dislocations are very close to the point where you're doing the curse, and you cannot move.
They cannot do it.
So the comment was from the previous question. This is for people that are online or for the video, since nobody hears questions. The comment was that if you have a small enough grain that your dislocations are interacting with the grain boundary, then you have a back stress that occurs. It becomes like a Hall patch type of a situation, and you get a harder apparent grain because of the interaction with the structure around it. Okay.
But if the boundary is CSL, then the dislocation can glide.
Right, so the follow-up question is, what if it's a CSL boundary and you get nice slip transmission through the boundary? All of those things are considerations. Yes. Slip transmission, absorption, reflection, all of those things are considerations of,
So basically find out is because of the high angle grain boundary.
well, of boundaries that become an obstacle. High angle grain boundaries might not become an obstacle depending on what your slip system is and how it's shared between the other grain. There's a lot of models for this also. Yeah. Okay, so we have a few minutes. And maybe I'll just save this for next time and we can talk about some of these distributions. So we've started talking about grain boundaries, and I've motivated that because of the SPARC focusing on triple junctions. And triple junctions are made up of grain boundaries. And eventually I would like to be able to say, this is the kind of things that we need to consider when we're talking about triple junctions. Right? So I'm hoping that collaboration between Washington State University and IIT Kharagpur will be able to do a nice contribution specifically in the triple junctions area. So a lot of the questions that you're asking about interactions with boundaries and those types of things, once we go to nanocrystalline materials, all of a sudden maybe triple line volume is going to be just as important as the grain boundary in these cases. So I'm going to stop there because while it's fun to steal Professor Masarovich's time, I'm well experienced at that, I've caught myself this time and I say, okay, we can get him set up and he can get going by about 11 when he's supposed to. So, all right? Good. Thank you. All right. And we should introduce Professor Banerjee, who showed up. He finally got here from the U.S. after his daughter's birthday.
Hello.
This Professor Banerjee.
Nice to meet you all.
I think Monday is when you start lecturing,
Yes.
right? So atomistic simulations and DFT. Are you going to lecture on as well?
Yeah, I'll cover a range of length scale all the way from angstroms to shy of micrometers, let's say. So, talking about DFT, molecular dynamics, and some Monte Carlo.
Good. Anyway, we're glad he's here.
Thank you.
We're quantification. Just switched. Do you want us to take a break now? I didn't know for sure.
He came and sat in between the students. So,
Introduced me already, so.
We introduced him briefly, but you can say whatever you want. You can.
yeah, means when we started, we introduced him. So, Shobhik Banerjee, Professor Shobhik Banerjee, he is here. So, let's give him a warm welcome. So, he will be teaching us simulation.
Please speak something, sir.
1, 2, 3. All right. Okay, thank you. But just let's. My slides are not showing. They are now. Very good. Good morning, everyone. So let me briefly remind you what we did last time. There is a little bit more of continuum mechanics, and then we are going to phase field models. Last time we defined strong form,
of the problem and weak form. Strong form had a differential equation, partial differential equation in the domain plus boundary conditions. Weak form was an integral form which included, in addition to our unknown variables, included virtual quantities which are purely fictional and could be, well, arbitrary. That weak form has two purposes. First, for finite element method, we need to reformulate our problem in a weak form because finite element method is based on interpolation. And if you are interpolating, it is much more accurate to integrate what you're interpolating than to differentiate. Derivatives always have much higher error than a function in all numerical methods. But integrals have smaller error. So that was one purpose. The other purpose is for complex problems. It is very often much easier and much more rigorous and much clearer, in fact, to derive your governing equations from the weak form. How does that work? First, you do balance of power, that is rate of energy. How does the energy change? You do the work, you take the heat, and from there, when you formulate it properly in terms of your unknown variables, then you can use that power balance. And here's how the power, this top equation, that's the power balance. So work of external forces, including inertia, is work of internal forces. Sigma are elastic stresses, plus dissipation. Sorry, sigma are stresses, total stresses. We will separate them later. Plus dissipation, and we said there are some dissipative variables, xi, and there is their power conjugate, psi, and these tau would be viscous stresses. This is also dissipative. So if you write that, well, if you write your power balance properly, then you can immediately transform it into the weak form using principle of virtual power. That is, instead of power expanded on real variables, such as velocity and xi dot, that is rate of change of the state variable, you introduce virtual velocities and virtual state variable rates, or test functions, as mathematicians would like to call them. And you write the same form, formally the same power balance as a principle of virtual power, which says that work of external real forces on virtual velocities is equal to the work of internal forces on, and these are internal forces now, we have that from power balance, on virtual rates and velocities. And from there, you immediately get your strong form. If you look at this expression here, this is, okay, this here is nothing but your Cauchy equation of motion. Because these quantities are arbitrary, and this has to be true for any possible value, any possible function v tilde and xi tilde dot. That means that everything that multiplies those functions has to be 0. So if you put the condition that this is equal 0, this is your Cauchy equation of motion. We are used to seeing it in this form, del dot sigma tensor plus rho b, b is body force, equals, so putting minus on the other side, rho v dot, or if you want dv over dt, right, that's my v dot. these are Cauchy equations of motion. Here, from this part, you get boundary conditions, right? In terms of tractions. Normal projection n dot sigma is the traction. And from this part here, you get the meaning of this physical meaning of this power conjugate psi. It has to be minus rho del potential energy over del xi. So we will use this. But before that, let me remind you, we did a little bit of theory of the finite element method. We introduced interpolation. How does finite element work theoretically? You write the weak form, you introduce interpolation. Well, interpolation functions like this. You write your variables, and this is linear elasticity example where our only variables are displacements. So I write those variables as a linear combination of nodal values and interpolation functions. And interpolation functions must be, interpolation function psi alpha must be 1 at node alpha and 0 at all other nodes. If you plot interpolation function psi alpha in 2D, say for 2D problem, it has value 1 here and it's 0 elsewhere. It need not be linear. It's just easier to draw it linear. And you do the same interpolation for test function. You throw everything into your weak form, and then you separate those coefficients that your computer can compute, that is known, right? And you get a system. Well, in this case, this is elastodynamics. You get the system of ordinary differential equations in time for nodal variables, nodal values of displacement. In quasi-static problems, this will go to 0, and elastostatics, only this remains. And in terms of, for elastostatics, you only have a k by u equals f.
You have to discretize also in time.
Sorry?
You have to discretize also in time.
Yes, but time stepping is done differently. We discretize space using finite elements, and for time we use all the standard time integration, time stepping procedures, Euler, backward Euler, midpoint rule, Runge-Kutta if you want. Finite difference is not good for time. Finite difference also works for space.
Okay.
Right. Finite elements replace finite difference. Okay. So, and I talk a little bit about those, about convergence of the finite element method, and we discussed that the main property which affects the convergence and accuracy of the finite element method is completeness of interpolation functions. That is, the highest complete polynomial interpolation function. So for example, 6-node triangle and 9-node quad have exactly the same completeness. So these are the terms that come in 6-node triangle: 1, 2, 3, 4, 5, 6. For 9-node quad, like this one, I have these additional terms, but they do not change completeness, right? Completeness is still 2. And based on the completeness theorem, the relative error of our finite element calculations behaves as h over L to the power k plus 1 minus m. K is completeness, m is the order of error. So error R naught is error in displacements, error R1 is error in strains or in stresses too. Right. So for linear elements, we have quadratic convergence for displacement, but only linear for strains and stresses. For quadratic elements, we have cubic convergence for displacements and quadratic for strains and stresses. This is very important. This linear is not good, right? Because if you write this h over L is mesh parameter, and this is the size of the domain, right? So as your elements decrease, so as the number of elements goes up, your relative error linear is 1 over n, right? In 1D. Quadratic is 1 over n square, and cubic 1 over n cube, right? So much faster. Okay, so I'll skip this example. Maybe I'll show it later, and I want to now derive finite element equations for incompressible linear viscous fluid. These are Navier-Stokes equations, well-known Navier-Stokes equations, using the weak form. So I will assume that my viscous stresses are given. This is linear viscous material. This is a viscous stress is tau. 1/2 of this is a deformation rate tensor. So this is 2 mu by tensor D, and tensor D is 1/2 V del plus del V. That is, it is the symmetric part of the tensor L, and L was velocity gradient tensor. This is our tensor L, V del. So L, just to remind you, in terms of components, is del Vi over del Xj on the basis Ei Ej, or we write it shorter, Vi comma J Ei Ej. So we add it to its transpose, take 1/2, and you get a symmetric tensor. Instead of mass balance, we have incompressibility condition. Now, we don't have constitutive equation for pressure, but this incompressibility condition is an extra equation which will give us pressure, because to fully determine stress, we need viscous stress, but we also need pressure, because this viscous stress is deviatoric. That is, if you take the trace of this stress tensor, tau 1,1 plus tau 2,2 plus tau 3,3, that will be 0. Why? Because it is proportional to deviatoric displacements.
It is V, not U.
Sorry?
It is V, you have written as V, so V is velocity.
Yes, velocity, yes.
So then tau cannot be stress. It is stress.
Yeah, this is viscosity.
This is viscosity. Okay.
Yeah.
Okay, then
Yes, mu is a viscosity. So it has units stress by time.
stress by time.
Yeah. So this is very standard fluid mechanics, but because it is standard, it is useful to see how we derive the equations. So so here's right away my weak form.
So I have a question.
Yes.
Little off-topic question. Like this during defining this yield criteria, we take the invariance in deviatory component.
Yes.
Because that the deviatory component changes shape and the hydro changes shape and the hydrostatic component changes the size.
You're talking about plasticity now,
Yeah.
right? Okay.
Actually, I want to understand the significance of the taking deviatory component.
Deviatoric strain changes shape, but it does not change volume. Right. So any symmetric tensor, stress or strain, could be written as a sum of two tensors, deviatoric plus volumetric. So let's take a tensor stress, sigma. Well, I can write that matrix sigma as a sum of sigma 1 1 prime, 1 2 prime, sorry, 1 2 comes here, this is 2 2, and so on and on. Well, this is deviatoric. Well, and the volumetric would be 1/3 sigma mean, 1/3 sigma mean, 1/3 sigma mean, right? So this is a mean stress. This is a where the mean stress is actually I don't need 1/3. I'll just define the mean stress as I'll put 1/3 here, right? 1/3 sigma 1 1 plus sigma 2 2 plus sigma 3 3, right? Now, if you add up diagonal terms of this one, they will add up to 0. So the trace of this matrix is 0. This is deviatoric stress, and this is volumetric stress. You can do the same thing for strain. This, well, if this was strain, this would only change shape, but not volume. And this would only change volume, but not shape. Well, in plasticity, plastic deformation is purely deviatoric because it's shear, right? Dislocations glide and you change shape, but the glide of dislocation does not change volume. So if you look elastic plastic solid and you load it with arbitrary load, elastic deformation will have full stress tensor, full strain tensor, both volumetric and deviatoric. Plastic deformation will be purely deviatoric. So, but stress does work on strain. It can be shown that volumetric stresses do work on volumetric strains and deviatoric stresses do work on deviatoric strains. There is no crossover. Those two works are independent, additive. So the proper power conjugate or work conjugate for plastic strain must be deviatoric stress. Because volumetric part does no work. Now, you can put it there, but it won't do anything. Right? That's why we only use deviatoric stress in plasticity. Same thing for viscous flow. Think of water. Right? You shear the water, you're not changing volume. Right? You get a flow, change of shape of your elements, but no change in volume. So and no change in volume is what is represented like this. And if you write this in terms this divergence of the velocity in terms of components, that will be del v1 over del x1 plus del v2 over del x2 plus del v3 over del x3, right? And that is the same, that is actually the trace of our tensor L, of this tensor here. The trace, sum of diagonal components. Well, that is 0, so no volume change. Okay, so we go straight to our principle of virtual power. External forces, inertia, oh, sorry, I'm here, traction, body forces and inertia is the same work of those external forces on virtual velocities or power expanded is the same as power of true stress, real stress on virtual strain rates, and I add Lagrange multiplier, this extra condition with Lagrange multiplier, P tilde. And for incompressible fluid, this will be 0, right? So then, this term is here. Here and there, well, this is material derivative, right? And it will have two parts. Well, it will have partial and this, well, convected part. When I substitute my stress has a viscous stress and pressure. So here's what comes from viscous stress. Here's my pressure by V del. And then if I write this sigma ij v tilde I comma j, I do the transformation which we did before. This is sigma ij, sorry, this is vji, right? Sigma ij vj tilde comma I minus sigma ij comma I by vj. So this term will then go to the boundary, and this term will remain inside, and what I will get, what I will get in the end are Navier-Stokes equations, which look like this. Let me share. These are Navier-Stokes equations, well known for fluid mechanics, plus incompressibility condition. So these are my governing equations. But meanwhile, I could also get finite element equations. If I introduce interpolation here for V and for V tilde and for P and P tilde, there's P and P tilde. My unknown variables are V and the pressure P. So I'll get well, two equations, two finite element equations. One would look like this with mass matrix, viscosity matrix, and there will be part which depends on external forces. This is this nonlinear part in terms of the velocity. and part that depends on pressure. These are all free terms. And I will get extra equations from which arise from incompressibility condition. But we don't need to really get into details. To conclude this part, if you have done that little homework that I gave you in the beginning, you should be able now to do this little bit more advanced problem, and it's a fluid mechanics problem. And let's make it 2D, right? So, well, it's not a sphere. Here it's a cylinder and infinite plates, and it's falling under the weight of gravity through the fluid, which is, well, something like water with a viscosity of 0.1 Pascal second. Weight 10 to the 3 kilograms per meter cube. These are rigid walls on the side. This sphere is rigid, so you will need to input, well, rigid boundary into your console. Now, this problem is rather difficult to start with. So I would recommend that you first start with. Well, it is difficult because as this ball falls down, you need to do remeshing, right? So you need to have a fine mesh here, small elements, and here far away you can have big elements, right, and bigger. And the further away you are, your elements could get bigger and bigger, because far away from the ball, all you need to represent is a parabolic field of flow, right? It's a it's flow through a pipe. That is flow between two walls, two-dimensional. So it's a parabolic distribution, and that's easily represented by by few finite elements, right? But here in the vicinity of the ball, you need to have fine mesh. So if to do ball dropping, you will need to do remeshing continuously, well, as the ball drops. Somewhat simple way, somewhat simple problem, which you may want to try first, is to take those walls to impose the velocity of fluid here and there, fix this ball, and then you have a fixed mesh, very fine mesh here, much coarser mesh here. You don't have to do remeshing, it's much cheaper computationally, and you you just give it prescribed, average velocity W, and see what happens, what kind of flow field you get here. You will get some vortices, and things like that. Then you may go to this more complex transient problem to mesh with adaptive meshing. Adaptive meshing is very important. If you recall those problems that I showed you before, the boundaries move, and within the phase field change, we need very fine mesh. So adaptive meshing is an important part of all these calculations. But I would first like you to master inputting the equations, such as these, into the problem for your unknown variables. Unknown variables here are vector V and pressure P. So you can first practice that and then try the problem with remeshing under gravity. So as problem number 2, you can try full, so this would be steady state motion, right? Right, you fix the velocity and just look what happens. And here you will really put no gravity. So no gravity. so for more difficult problem, start with that's a full transient problem. Put the gravity in, right, and let the ball drop. So if you you may try, or disk, right? You may try a lighter disk or heavier disk and see whether you reach steady state velocity in a reasonable time. Okay, and with this, I would switch the topic, and I will start talking now, finally, about interfaces. Yes. There is a question? Uh-huh. If you're talking about fluid mechanics, okay, question is, can you explain how knowing, understanding these equations in such details can help in the field of metallurgy and materials research? These particular equations are fluid mechanics. So, in metallurgy, you get fluids in melting and solidification. But this particular problem that I've given now is for practice, right? That's a simple problem. But you do have fluid mechanics, and we will see soon equations just like this for phase field model, which includes melting and capillary flow. So we'll get there. We will soon get to very relevant application when you have molten metal flowing under capillary and gravitational forces, and then solidifying in very non-homogeneous microstructure because of segregation. So you will see that problem very soon. Okay. Any more? No, that was the last question. So we can move on. Okay, let's talk about interfaces. And it's important with interfaces to understand what is it that we know and what is it that we don't know. For our understanding of interfaces and the language that we use is mostly due to Gibbs, turn of the century, well, 20th century, who decided to, who introduced the concept of interface energy. Well, and how does that work? Well, consider two crystals, and let's look at the atoms. Let's plot average energy of atoms in each vertical line, right? Well, along this line, average energy will be this. So these are two crystals. They might be identical, might not be identical material. In fact, but for each column of atoms, I can plot, or each plane of atoms, I can plot some average energy. So what we notice is that energies will be increasing as we approach interface. So on one side, we have pretty much constant energy per atom. On the other side, constant energy per atom. And here we have changes. So what Gibbs said, let's take all this extra, and dump it onto the surface. So instead of, this is so-called sharp interface model, or the concept of Gibbs excess quantities. So that's where concept of surface energy or interface energy comes in. we denoted gamma energy per unit area. So we say, we assume that up to the interface, our crystals have uniform energy density, and then there is certain energy associated with interface, with mathematical plane, which has no thickness. Now, I can do that for many other quantities. I can do volume per atom, right? And this is Gibbs excess volume. Entropy, enthalpy, other thermodynamic potentials. So I can do that for any quantity. I can dump those differences, which are in fact gradual near the interface. I just dumped it onto mathematical plane. Okay, well, so let's. So if I want to, if I have a body which consists of two different domains with an interface, like here, I can write the total free energy as energy density in one integrated over the volume of one, energy density of two integrated over the volume of two, plus interface energy. Now, in general, interface energy is greater than zero. Why? Can anyone tell me why?
It has to create the extra surface.
I'm sorry?
It has to create the extra surface.
Yes, but how do can you make an argument which will convince us that atoms at the surface will have higher energy than atoms in the bulk?
They have free bond.
Huh?
Free bond in one side.
The very fact that atoms crystallize means that they want to have that crystalline neighborhood. So that's the low energy configuration. If they don't have that neighborhood, that's the higher energy configuration. So that's why our interface energy is always positive.
And the kinetic energy is always positive.
Well, kinetic energy too. Yes, yes.
And only the potential energy could be negative.
Yes, potential energy could be negative, but interface energy will be positive always. Interface energy density, this gamma, this will always be positive. Now, for solids, we need to distinguish between interface energy and interface stress. People working with fluid mechanics usually don't know the difference. They call it interface energy or interface tension. Well, these are things that are numerically equal for fluids. They are not numerically equal for solids. So, what is in, yes?
Are you taking a sharp interface?
Yes, sharp interface. Now we are talking sharp interface. So, meaning that all that extra energy is dumped onto mathematical plane without thickness. Gibbs concept. Okay, what is a stress? Stress is a work conjugate of strain. That's what does work on strain, by definition. So let's see, work is change of energy, right? So let's see what is the change of my interface energy is gamma interface energy density by the area. So if I change this, it will be gamma dA plus A d gamma, right? Both things change. So now this dA is A, this dA is A d epsilon ij, where epsilon ij are surface strains. So here indices I and j go, just take values 1 and 2 because we take coordinate system 1 and 2 is in the plane and this is 3, right? 3 is normal to the plane. Now I'm stretching this interface, right? So this d gamma is it depends on strain, delta epsilon ij, d epsilon ij. So when I substitute this, first I can assume that interface area does not change with shear strain, right? When I do shear, so this will be in fact delta ij d epsilon ij. So delta ij d epsilon ij is d epsilon I, or d epsilon 1 plus d epsilon 2, right? So I have delta ij d epsilon ij by gamma, and I pull out a and d epsilon ij, and I have this expression for my interface stress. This is my, and let's call it Fij. So on this interface plane 1, 2, well, I have stresses F11, F22, F12, or F21, right? Whatever you want. They are still symmetric, right? So these are interface stresses. This is interface plane here. This is axis 3. Axis 3 is vertical. This is axis 1, for example. So, is there a question? No. My interface stresses, first, this is not just tension, right? This is a full tensor in 2D. There could be shear, and normal stresses could be different in different directions. There is a part which is for normal stresses, for sigma, for F11 and F22. There is a part which is proportional to the strain, to the interface energy, but there is also part which is not proportional to gamma, but change of gamma with strain. Now, those for fluids, this part will be 0. Why? Because when you stretch interface between two fluids, you are not really stretching atomic bonds. You stretch, and atoms in fluids are mobile. So new atom pops in on the surface, right? So there is no bond stretching. So this is 0. Gamma per atom remains the same. When you stretch the surface, you change the number of atoms at the surface. Yes?
So just wanted to confirm, the delta here is the chronicle delta.
Yes, chronicle delta. Yes. So for fluids, this part is 0, and my interface energy is the same as surface tension. But for solids, these surface stresses depend on orientation, and they may be positive or negative. There is no law which prevents them from being negative. Okay, so, well, we want to simulate something, right? And say we have a case like the one shown here. How am I doing with time? Just enough time to introduce phase field. What's the problem with doing simulation like this with sharp interface? Say I have two precipitates, and this shows you, well, two different simulations. In one case, this is diffusion controlled phase transformation. So in one case, material, the red material diffuses through the blue one, and the right-hand side precipitate will eat the left one, right? Well, on the other case, they will merge, as shown here. Now, imagine if you have to do this with a sharp interface model. First, you have a mesh. Well, you have two domains, right? 1 and 2. Well, you have a mesh for domain 2, mesh for domain 1, whether you do finite element, finite difference, whatever you do. But then you have to track the interface. And you have to decide what is the motion of the interface. Well, to simulate motion of the interface, you need a constitutive law which would connect your normal velocity to temperature, stresses, to velocities in the other domains, curvature of the interface. And even if you can do all that, then you need to do the business of numerically tracking the interface through your domain. And that interface tracking turned out to be a very nasty numerical process. Extremely expensive, very often not feasible, and specifically not feasible when you have topological discontinuities. And this is topological discontinuity. You have two particles here, and then here you have one particle, right? Different topology. What's the criterion for changing topology? When do they coalesce? See how foggy all that is. You have to make loads of assumptions there. And then you have to, even if you manage to deal with that theoretically, dealing numerically with this transition from this shape to this shape with sharp interface model is all but impossible. People have come up with solutions for special cases, but only when you know what is going to happen. What we need is a method which will simulate and tell us what is happening, not method which will simulate what we know what will happen. So tracking mathematically sharp interface is feasible only if you know what is going to happen. Then you can come up with an algorithm to do that. So that is why phase field model is necessary. So what is a phase field model? And here's it's a mathematical trick. Yes?
Topology means basically shape, right?
Yes. So you can call it topology, or you can use the word connectivity. So topology is discipline which deals with qualitative geometry. Sphere and cube are topologically equivalent because they're both, there is one body and it's closed. So it doesn't matter what the shape of sphere has corners and edges. Cube has corners and edges and sphere doesn't. But they're topologically equivalent because they're one. And they have no holes. They're one body with one boundary. And they have no holes. Now, material A, material B. I think this was copper and nickel. No, copper and aluminum in different phases. One phase and the other phase. So also topologically, a donut is topologically equivalent to your coffee mug. Because it has only one hole. Think of your donut has one hole, coffee mug has one hole. So these are all, you can change from donut to coffee mug with continuous motion of surfaces. But you cannot change from sphere to a donut without punching it. That's discontinuity. That's topological discontinuity. You have to create that hole. So here we have topological discontinuity, two bodies, and now we have one body.
But all these bodies have only one surface. There will not be two balls, but there could be many balls. But
Yes.
all these balls have one surface.
As long as they're connected.
As long as they are disconnected.
Yes.
So, but when even two connects, they will have also one surface.
Yes, but you will well, they will have a hole.
They will have.
Right. The question is. Well, that would get us way too much into rigorous definition. Let's stay with intuitive description of topology. Well, things can get more complicated. But basically, we need to solve a problem numerically how to have two interfaces coalesce, right? Two bodies becoming one. So here's the short description of the phase field model. Well, here's how it works. For sharp interface model, I write energies of two connected bodies, F energy of the one body, energy of the other body, and interface energy, right? So, can I make this, can I pretend that this is all one domain, one mathematical domain? I can. If I, instead of having this energy associated with the interface, I will define phase variable, which is one in one domain, one in the other domain, and over some interface thickness, it changes the value from 0 to 1. So instead of a step function for sharp interface, I will have gradual change within some thickness h. So then how can I write the energy? I will write the energy as energy density as a function of phi, where this F will be equal to F1 when phi is equal 0, and F2 when phi is equal 1, right? But in between, it will change gradually. Between, I can interpolate. But what shall I do with this? I need something that only exists in that interface. Well, it's the gradient of phi that only exists there. Here gradient is 0, here gradient is 0. Gradient is non-zero only there. So I will represent my interface energy as some coefficient, kappa, and one half is for convenience, by the gradient square, y square, because my interface energy has to be positive, right? So I can make this energy equivalent to this one. And as I formulate my model, I have to make sure that when this thickness goes to 0, as h goes to 0, this energy, let's call this energy F phase field. When h goes to 0, my F phase field has to go to F sharp, has to converge. For h not 0, I'm making small error, but I can control that error. So any other parameter, viscosity, elasticity, say any parameter p can be interpolated. When phi is equal 1, well, it has value P1. When phi is equal 0, it has value P2. In between, I could just do linear interpolation.
So what is this phi function?
It's a phase field function. Yeah, and we don't know a priori the distribution here. We just know that it's 0 here and 1 here, and within this range h, it changes gradually. The actual shape of that will come from the solution. So our phase field variable becomes unknown variable in our problem, right? We will prescribe initial distribution of phases, and then we will let them evolve.
So two more questions. Like I could not understand why there is half.
Just for convenience, you don't have to put it there. You can just put kappa here. It's convenient for later derivation. You can call all this kappa, right?
The second thing is you told that the square is there because we want the surface energy to be positive.
Yes.
But well, in that case, we can put the power as 4 also. In that,
Yes, we can, and it can be shown that it will not yield appreciable results. It's not necessary. Because, well, keep in mind, you can only make things as complicated as your background knowledge is. What do you know about the interface? You know one thing, interface energy, right? You don't know much more. So if you keep adding terms there, you could add power 4, but what physical quantities are going to match it to? Right? You need to match interface energy. So one thing to match, well, one coefficient, kappa. Right? You can always make things more complicated, but you don't have the information. Yes, we always go for simplest possible that can be measured experimentally, and experimentally you measure just one quantity, interface energy. Okay, I'll stop here, and we'll continue with the phase field model after the break. Say 5 minutes. Yeah. 1, 2, 3. Working. Okay. So let me first remind you of what we have done. Well, just to summarize this. First thing to remember, even if you were very much confused with all those equations and weak form and all that, important thing to take home from there is this statement. If I have a energy balance of energy rates, I have everything. From there, I can derive all the governing equations. That's the important takeaway. So, as I'm formulating phase field model, I will do my tricks on the energy. If I can write energy properly, everything else will follow from there. And this is what we do with energy. Because we don't like those sharp interfaces, they're bad numerically and bad theoretically, we make them disappear. We smoothen out the differences, but the most important part is how do we write energy. And the last thing that I have shown here is that you can write sharp interface energy, which consists of 2 volume integrals and 1 surface integral, as a single integral, where you assume that your energy density is a function of the state variable, of the phase field variable phi, taking the values for the phases 1 and 2, where phi is 1 or 0, and the term that is quadratic in the gradient of phi and which only exists inside the interface, that is here. Right. Now, there are 2 new things that have appeared here, 2 new parameters. One is this kappa, and one is this thickness h. Right. On the other hand, there is one more. There is one thing that we know, and that is our total interface energy. This quantity here is known to us. So, how shall we write this free energy density? This is energy density per unit volume as a function of phi. Well, we let's say this is the value for phase which corresponds to phi equals 0, and this is the value for phase which corresponds to phi equal 1. If I just connect them, then everything will automatically go to the lower energy. So I have to physically and mathematically, I need an energy barrier, which I will call delta F. So this energy will be double well potential, which has values which correspond to the phases here. Much experience, tells us that it doesn't matter how whether this is quadratic, cubic, or higher order. What matters is this maximum value only. So, and that is our second new parameter. So we have new parameter kappa, new parameter delta F. On the other hand, we have physical quantity, surface energy, interface energy, and we have computational quantity, interface width. We will show later how they are related. But for now, Oh, I'm sorry, Dave is not here. Well, he'll be thrilled. He said that no presentation is good unless it has some micrographs. Here are some micrographs. These are few examples of interfaces. The point is, interfaces tend to, well, in reality, interfaces tend to be diffuse. They are not sharp very often. Now, that is often used as a justification of the phase field model, but what I'm trying to tell you here, it is not a good justification. It is qualitative. But quantitatively, we never really do that. Because if you look at the thickness of this interface in, this is silicon, 2 grains of, I think this is amorphous silicon, and this is crystalline silicon. My interface is what? Nanometer, 2 nanometers? I don't have thermodynamics there. I don't have a sample. There's no statistical mechanics. Whatever happens there is not truly representable by continuum theory. So what I really have from interfaces is interface energy. I have Gibbsian sharp, that's what I can get from experiments. Everything else is speculation. So physical arguments that real interfaces are diffuse in some sense is there, but one should take it with a grain of salt qualitatively. As an aid to intuition. In practice, computational interfaces rarely, and I think never, I have never seen an example where people have done computations where the computational interface width corresponds to the physical width of interface. There may be some. I have not read all the papers that are out there, but I have never seen one. And then the interface propagation happens by discrete atomic events, and in that thin interface we really don't have statistics to make continuum theory represent physical reality. So instead we should follow mathematical argument. Phase field is a mathematical tool, mathematical trick for computationally treating evolving interfaces with topological discontinuities. That's a mathematical trick for making multiple domains one domain. That's what we're really doing, and smoothing out those interfaces. So the main criterion for validity of the phase field model is, in the limit of zero interface thickness, it must converge to the sharp interface fields. That is, energies, stresses, everything must converge to the sharp interface solution. And if we can show that, then we have a valid model. Okay, so let's now discuss the parameters of the phase field model. Let me just see the time. Okay, I'm good. So the parameters of the phase field model. Well, here's how it works. Let's express interface energy. I have my energy density as a function of phase, and I'll look at the interface at 0, and I'll integrate from minus infinity to infinity. And from that, for my total energy, I will subtract the energy of phase of the two phases. These are the energies of the two phases, right? And that will give me interface energy. So, and if you look at this curve, that will be integral of this delta F, right? Because my phi goes, well, I'm subtracting this part. This is the area of this trapeze, right?
So this minus infinity plus infinity along the plane.
No, no, normal to the plane. So here, this is my interface here, and I'm integrating from minus infinity to plus infinity.
Slides.
Yeah. Oh, we will not see slides. That's a problem. Tech guys. Okay, slides were not there for a moment. Okay, let's see what. Okay. So, what was I saying? Yes, this is the interface for x equals 0, right? And I'm integrating from minus infinity to plus infinity, right? Normal to the interface.
So like minus infinity to this minus h by 2, it will be 0. Then again from h by 2.
No, I have to subtract. See, this from minus infinity, phi is 0. So this has the value of energy density in the corresponding phase, right? So I have to subtract this part, right?
Like F is volumetric free energy, right?
Yes,
Energy
yes,
requirement volume.
yes.
But then we are getting it with gamma. When gamma is
That's a surface energy, right?
sir,
Yeah.
okay, the total energy is not like
So what I need to do here, I need to compute total energy and subtract the bulk energy. What remains is surface energy.
it's bulk energy extensive property, not the surface energy per unit area. Gamma is not like that. Or is it intensive property here?
I don't understand your question.
Like this gamma,
Yes.
its unit is joule or joule per meter square.
Joule per meter square. Yeah.
It's intensive property.
Yeah, joule per meter square. Yeah.
And sir, this phi, can we think this composition is one of the example of this phi phase field variable.
Yes. What about phase field variable?
Any example of phase field variable? Like, can composition be a example of?
You have two phases, right? You decide. At this phase, my phase field will be 0, and at this phase, my phase field will be 1. Whatever what your phases are. You can talk about two fluids, immiscible. You can talk about well, precipitate in a crystal. Your grains in polycrystal, each grain can be one phase, whatever you want. Think of it as one material and the other material, right? So you assign phase field to this material.
Like phase fraction.
I don't know what you mean. Phase function. Yes. And when phase field phi corresponds to my grain of copper, and when that function has value 1, I'm in the copper crystalline grain. When it's 0, I'm not there. Yeah, it's something else. So it could be, well, whatever you want.
Sir, it's supposed to be like a cascade. So if it goes to
I'm sorry, I don't know.
Like casting, like if you increasing the temperature, first the solid into converted into a liquid, then again it will be solidified into the solid. So
Yes.
what is the phase field function can you use?
If you want to describe your all solids, if you have melting which is which happens at a single interface, right? You would all solids will be phase function, let's say 1, and liquid will be 0. If you have to look at if you want to look at non-homogeneous melting, where you can have melting of different grains, and then you have different pieces of solid floating in the melt, then each grain will have its own phase field, right? And fluid, liquid, will have its own phase field. You could have multiple phase fields, right? But we are looking now at the case where you have only 2 phases. When you have 2 phases, you only need 1 phase field, right? But when you have multiple phases, the most convenient way is to give 1 phase field to each phase. Yes.
Is it applied to any electrochemical cell where
Any
electrochemical cell
electrochemical cell.
where under electric field there is liquid electrolyte and solid electrode and
Yes, yes, yes. The main thing would be to write the potential energy, under electric field and without it, and in between you would have phase transformation, right? 2 different phases. Any more questions? Okay, so I want to express my interface energy in terms of my phase field parameters. So, I will compute the total energy. I'm thinking of 2 solids going to infinity and just having 1 flat interface. And because everything is the same in y and z direction, I'm only integrating in x direction, right? Well, you can multiply everything with the unit area if you want. This is the total energy, this one. Integral from -infinity to infinity. But I need to subtract bulk energy of phase 1 of the left phase, where phi is 0, and bulk energy of the right phase. And this is what they are, right? When phi is 0, I only have this term. When phi is 1, I only have this term. But this really is this area of this trapeze here, right? I'm actually integrating delta f, this difference here, and when I do that, then let me skip all the mathematical details. You can find this in the papers, but you will find that your
0 to 1, not infinity, -infinity to infinity.
sorry?
What is the interface energy? The phi is varying from 0 to 1 only.
Yeah.
So you are integrating the difference.
No, this is integral over x, but you can transform this integral. Phi is function of x, right? So you can, in the end, you will be integrating over phi. Right, this is integral over phi. This is when you transform the integral over x into integral over phi. But in the end, there's no point in getting through all the algebra. But in the end, you will get an expression like this, that your interface energy is 2 kappa, function delta phi, and function delta phi is this difference, this here. This is delta phi. Sorry, delta f. This difference here. An integral phi going from 0 to 1. So basically this area here. Well, square root of it with a coefficient kappa. So, well, if you take this delta f of phi to be 4th order polynomial and symmetric, so it's a polynomial which looks like this, right? This is 0, this is 1, and this is delta f maximum. From here you will get the relationship of this delta f maximum and our parameter kappa to our physical quantity, interface energy, and our computational quantity, interface thickness. Very simple relationships. So, any questions here?
Sir, the simple form came after the assumption, or it came for whatever mathematics we did?
It's a mathematical derivation. You need to use some.
Main question, like, what are the assumptions underlying this simplification?
Only that this function delta f is a 4th order polynomial, and you really need well, 4th order. You want it to be symmetric. Let me see if I have somewhere plotted that. Yeah, something like this, right? Well, if this is a 4th order, then this delta f is our delta f maximum, right? So if you do the 4th order, then you will get. I mean, you cannot make it cubic, right? You see, you have three extrema, two minima and 1 maximum. So you have to make it 4th order. So if you do 4th order, and this is the value, well, of the maximum, then the relationship between our parameter kappa, these are phase field parameters, kappa and delta f max, right? And I can directly relate those to the physical quantity, interface energy, and my computational quantity, which is interface thickness. No other assumption, just that this is 4th order polynomial. It turns out that, let me just jump ahead a little. It turns out the shape of this function doesn't matter much. You can, well, instead of this, you could do straight lines. Vertical lines, nothing will change. Still, the only relevant parameter is this maximum. So that's why we typically use this 4th order, because it's smooth, and if you make it with corners, you get computational problems. Okay, so let me. I'll have to erase all the.
Phi is changing when p is less than 0.
I'm sorry?
When p is less than 0 and p is greater than 1, the phi is still changing. It is function of p, so it is some function of p. Okay.
where phi will never get smaller than 0.
Yeah, so P is but Fi is changing. Even P is less than 0. So it is 0 everywhere. P is beyond.
Yes,
zero
yes.
is zero.
No, these things well, this point will never exist. Right. This is just formally to write fourth order polynomial, right?
The P is 0, beyond P is going to be 0, it is constant. And then the step function, P0 and then P1.
No, step function, that's a sharp interface model.
Okay,
That's the limit where this h goes to 0, right? But in phase field model, we have a finite interface thickness h, and we have gradual transition from 0 to 1.
So d phi by dx exists only between P0 to 1. d phi by dx, C multiplied by d phi by dx square
Yes,
exists only between P0 to P1.
yes, yes.
Yeah.
So it exists only in this interval h. Elsewhere it's 0.
So it is 0.
Yeah.
But what is the separation? The distance is not visible. How much is distance?
H.
H.
Whatever you want.
Mm.
See, you decide how accurate you want your calculations to be. Well, as a general rule, h should be much smaller than the smallest radius of curvature. Let me, here's the example. So if this is the smallest radius of curvature that you expect, you should make your h, h here is this white area, right? So, well, at this point, h is becoming, as this little ball is shrinking, at some point you lose accuracy because your interface thickness becomes comparable to the radius of curvature. But in general, if you have radius of curvature at this point, and this is the radius of curvature, your h should be much smaller than the radius of curvature. Now, well, sometimes you will have to do that iteratively, right? Well, in these calculations, we can think of these as being well accurate. Now, whatever happens in between this stage and this stage is not very accurate because here radius of curvature is becoming much smaller and my h is still the same, so I'm losing accuracy there.
But here topology is changing. So
Yes.
our model, the stress field model, is it valid or
It's still valid. It's just less accurate.
less accurate?
Yeah, because this condition is not satisfied anymore. So I mean, the phase field model works. It runs, and it does represent approximation, but the smaller the h, the approximation is better.
The smaller the h.
Yeah.
The h will depend upon the field, the gradient energy.
Yes. 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 So as h decreases, you are approaching the step function.
Sir, just a quick question.
Yes.
Like, go to that this slide.
This line.
Say that this mention this color coding is of concentration, right?
No, sorry, color coding is?
For concentration of elements.
Yes. Yes.
But if we see a blue reference, it shows -1. So how can we get -1?
Oh, sorry. these are calculations done maybe 15 years ago, but by one of my students, and phase field goes between -1 and 1, right? Well, our decision to make phase field from 0 to 1 is arbitrary. I could make it -1 to 1. Well, if it's more convenient. Well, it's the same thing, right? So in my well, transition region, H, well, I could change field from -1 to 1, or I could change it from 0 to 1. The details change, well, algebra, but it's the same principle, right? So this is just, we did those calculations. Actually, my graduate student at the time liked to make it -1 to 1. I don't know why, but he liked it that way. Okay. So, well, important point here, phase field parameter, this delta F max and this kappa can be uniquely determined, this is one-to-one mapping, from interface energy and prescribed interface thickness. So that solves the problem, well, of parameters. The choice of interface thickness typically depends on the computational power that is available to you, right? If you're working well, on a supercomputer, you can make it very thin. But if you're working on a laptop, you will try, well, you'll do rough calculations first, right? With a thick interface. Okay. But our interfaces move, our phase field moves, but at some point there should be an equilibrium. Sometimes interfaces are in equilibrium, right? So let's see how equilibrium in phase field looks like. Well, equilibrium will be determined by energy minimum, right? So if this is the free energy of the system, that's some function g of phi and gradient phi, or I have integral of f, this is energy density per unit volume, right? And this is this represents my interface energy. I find well, I need to find 0 of the variation, of the variational derivative, well, of that function. So standard calculus of variations, the variation of f will be del f over del phi, delta phi, and then I have a variation of the gradient. You ask why 1/2? Well, here's why 1/2, right? Because I have square here, right? And when I do variation, well, 1/2 goes away. That's the simple answer to your question about 1/2 here. So this is the variation, and then see this one is phi comma I by delta phi comma I. So, well, I can write this as phi comma I phi comma I minus phi comma I delta phi. Do you agree? You all with me? Yeah, this is gradient of phi. This is gradient of delta phi, right? But well, I can write this as phi comma I minus phi I del phi, right? This is just a well, derivative of a product, right? Yeah, but well, I can do it in components. Well, summation is implied. I can do component by component. So this one is written like this: gradient of phi by delta phi divergence. Right. This is divergence of a vector here, and this one is Laplacian by delta phi. Now this divergence will go to the surface, and it will become n dot delta phi, right? And this Laplacian multiplies delta phi, so we'll go, well, it will go with this term. So I have del f over del phi minus kappa Laplacian of phi, multiplying delta phi in the volume, and I will have kappa normal gradient of phi, this is normal gradient of phi, by delta phi on the surface. So this has to be 0. Well, to have minimum. So that tells me that this quantity has to be 0, and I will call this quantity phase field potential. And this equation tells me that phase field potential has to be 0, and this gives me boundary condition in terms of normal component of delta phi, or boundary condition, well, in delta phi, because, well, I have a part of boundary where phi is prescribed, there delta phi will be 0. On part of the boundary where phi is not prescribed, delta phi will not be 0, but this normal component of the gradient must be 0. Now that we have a concept of this phase field potential, we can distinguish two classes of phase field models. One is non-conserved phase field, or so-called Allen-Kahn models. Sorry?
A quick question.
Yes.
Like this m not equal to 0 is minimization of overall energy, right? Just like del f is equal to 0.
Yes, that's the minimum of total energy, right?
That's
So
why how we are achieving equilibrium.
yes, that's equilibrium. But this m is not always 0, right? During the process, if m is 0, nothing is moving, right? Equilibrium means static, no motion. But during the process, that m will not be 0, right? But that tells us that m is the power, m is what does work on change on the phase field. And when that is 0, phase field stops, right? So that motivates this non-conserved phase fields. So that's a phase field in, say, matricitic transformation, melting, solidification. My phases are, let's say, solid and fluid, where none of those is conserved. But if I have a flow of fluids, right? Two fluids mixing, well, not mixing, but flowing together, and I'm using phase field to describe them, then my phase fields are conserved, because I have only so much of one fluid and so much of the other fluid. They're both conserved. So I have to distinguish how I deal with conserved and non-conserved phase fields. If I have a non-conserved phase field, I will write a constitutive law which will make rate of change of phi proportional to this potential, this. there will be some mobility coefficient, but that's a constitutive coefficient, which I can measure experimentally. I can get it from atomistic simulations. But a rate of change of phi will be proportional to the think of this m just like chemical potential for diffusion, right? Or diffusion potential.
Or mobility.
No, mobility will be coefficient in front of it, right? This means proportional, right? So I will write phi dot as minus mobility coefficient, let's call it b by m, right? So this is mobility, and this is my driving force. These are so-called, well, Allen-Kahn models, and that clearly gives you a second-order partial, because see, this m has a Laplacian here, so second-order PDE, and it's a diffusion type equation. Conserved phase fields are much more difficult. If phase fields are conserved, then I have to have a flux, right? My rate of change of phase field comes from a phase field flux. I can only transport my phase. I cannot create it out of nothing, right? Q is a phase flux. If phase is conserved, that it can only come to this point through flux. It cannot be created at this point. So that conservation law tells you that you will have divergence of the flux here. Divergence of the flux will give you rate of change. So the difference between how much goes out and how much goes in, that makes your phase field conserved. Then I will make my flux proportional to the gradient of the potential. So I need a vector. Flux is a vector. So I will use this potential and gradient of the potential. So going towards lower energy, that's the direction of the flux. And notice if I substitute this here, I have two more spatial derivatives, gradients. M has the second one here, and I have two, on the top of that I have two more gradient. These are so-called Kahn-Hilliard diffusion equations, and they will be fourth order. So it's a more complex diffusion type equation. Both those give you, both those are nonlinear diffusion equations, and nonlinearity comes from here, right? This is nonlinear function, and this partial will be nonlinear. So these are both nonlinear equations. For non-conserved phase field, I have second order diffusion type equation. For conserved phase field, I have fourth order diffusion type equation. Sometimes these are called diffusion reaction equations, where those nonlinear terms here can be interpreted as reaction. In chemical engineering and chemistry, in the early 90s, these equations were very popular, and you can see a bunch of papers showing all sorts of patterns emerging from those nonlinear equations. And indeed, if you allow yourself freedom to write equations like this, you can get just about any pattern from there if you play with parameters. Those patterns obtained in a computer are not to be taken too seriously, right? You need to get your physical parameters right and then see what's happening. Okay, and that's probably a good point to end this. Let me just see what's next. Yes. We will now start. Well, next time we will do a problem in fluid mechanics, and then we will do solid mechanics after that. So next time there will be melting and flow, and then the last lecture will be diffusion in solids, grain boundary growth, triple junctions, well, quadruple junctions, and things like that.
I have a couple of questions.
Yes, go ahead.
Like in the beginning of second half, you told that if we can take care of energy balance equation,
Yes.
then we that's the bottom line.
Yes.
This is true for only phase field modeling or in general?
That's true in general, but it's particularly true for phase field because it's hard to think of any other way of getting to governing equations. For other problems, non-phase field problems, usually there is a way to make physical arguments, to use momentum balance, to make different assumptions, to somehow squeeze into your, to get in the end, well, governing equations. But because phase fields are abstract, value 1, value 0, right? They don't have concrete physical meaning. They just mean that it's a phase or it's not a phase. It's very difficult to work with them other than rigorously from energy. So that statement is true in general, but it's particularly important for phase field formulations.
So the second question is, you told that experimentally we can determine this interface energy.
Yes.
So can you tell how do we do that? How do we determine experimentally the interface energy?
People get interface energies from well, first surface energy. You can that easily for fluids, right? You melt your solid and you, well, droplet hanging, well, surface tension will be equal to well, to surface energy. Interface energy between two grains is more difficult to I think there are calorimetric experiments which measure drop in potential energy with grain growth. You know what? I don't know. We have to ask Dave that. He's an experimentalist. So let's ask Dave that now.
Can I ask more questions?
Yes.
Actually, non-conservative phase field
Yes.
means are we assuming that they are completely miscible and not forming any new phase other than phase 1 and phase 2?
To formulate phase field formulation, you need to have well, you need to know what phases are being formed, right? I mean, you can because you write you need energy density for each phase, right? So you need to know well, a priori, what are your possible phases. So in your simulation, some of those possible phases may not form, but you need energy densities for all of them for your energy function. So you need to know a priori at least what are the possible phases. You don't need to predict which one will form and which one will not, but you need to know what the possibilities are.
So last question.
Yes.
Like for this non-conservative phase field,
Yes.
you told phi dot is proportional to minus of m.
Yes.
It may be silly, but I think like the phi dot should be proportional to minus of m dot because this rate of field change.
No. Think of M as energy, right?
Yeah.
Well, as a driving force.
Sir, m is driving force or change in m is driving force?
Let me show you. We actually did a derivation which in the previous well, in the previous lecture. Where is it? Where is it? Not here, a little bit earlier. No, this is finite elements. Ah, here we go. So, see, remember those variables C, right? They have a power conjugate, rate conjugate, right? Psi. And we showed that psi is psi is rate of change of energy by your variable. So you would write a constitutive law for C dot here as some mobility, let's call it B, and minus del U over del C. But this is your M. This is what we call M. Right? Clear? Yeah. See, that is part of why I did all this before in the previous lecture. Okay? Any more questions? Yes?
Sir, you talked about the surface energy.
Yes.
So to create any surface, we require some before that energy, that is volume free energy. So why we are not focusing on volume free energy? Because to create a surface, that surface energy should come from the volume free energy.
Surface energy, right, think of two volumes joined, right? When you say volume free energy, we're talking about energy density, energy per unit volume. So for two volumes, and let's look at a slide here. Oh no, I didn't close it, I think. Yeah. So for two volumes, you have well, energy density here and energy density there. But that's think of energy density as energy per atom and then number of atoms per unit volume, right? But energy per atom is different on the surface. So surface energy is the difference in energy between atoms that are at the surface and close and atoms that are in the bulk. That's the difference between those that atoms on the surface which don't have a nice neighborhood, low energy neighborhood, and those atoms which have nice neighborhood. That's what surface energy is. I hope that answers your question. More questions? Anything from online? Nope. These are old ones. Okay, so that's it for today. Thank you all. Now I have to untangle myself.